Good morning, students. I hope everybody's doing well, enjoying this nice cold weather. I guess we're having our winter moments again. No telling what next week will hold for us, but it's nice to have a little bit cooler weather. I don't want anybody to get sick, so please take care of yourself. And as I've always said before, taking those extra precautions make all the difference. If you go out, have your mask, be very vigilant about that. I think as the rates continue to go up of incidents of the COVID, we need to be more careful. And I'm doing it myself. I'm kind of stubborn, but when you go out, please be very careful. I want you to preserve your health. Because you can't do math if you're sick, and so I don't want you to be in that category. Now, I just want to let you know what we finish through today will be the end of the test material for test 4, which is going to occur at the beginning of next week. So it'll be a lot less material, just the end of the trig work, and then what we covered today with the parabolas and the ellipses, very basic material. But I wanted to go ahead and get in an assessment before the Thanksgiving time that you have off. You've got homework to do and things of that nature. And so I want you to be able to get that assessment in before when we come back. We'll finish up the work that we have in the class and then get set up for the final exam. I just don't want the time to be really crowded, and this way I think you can maybe enjoy your break a little bit more. So keep that engine running with doing your work. I know you're tired, but let's have a strong finish until before the break, and then when you come back, you'll have enough steam, hopefully, to finish out well. So just keep that in mind. When it's over, you can prop your feet up and take a break. Unless you're going to do the 3-week mini, but I don't recommend that. Everybody needs a break. Now, what I want to do before I start with the parabolas, the conic sections, is I want to do an example that was asked during my conference hours, a trig equation, and it's actually a very simple equation, but I just want to show it to you because I thought it was an interesting problem. Similar to some of the ones that I've done in class. So I thank my student for asking about this. So for this particular example, let's just move this over a little bit. It looked pretty simple, but it had mixed arguments in it. So basically the problem said solve in 0 to 2 pi. Lots of times the WebAssign will just say solve for all solutions and then say, well, list the solutions in 0 to 2 pi. So in this particular case, you can think all solutions and then dial it back, or you can just look at this and say, okay, well, I'll just stick to the unit circle, so to speak. And this is what it looked like. It actually allows us to use one of these really neat identities that we had. We had a lot of identities last week, and then we saw how they worked with the equations. And so that keeps us busy with the arithmetic of the unit circle. And also, ladies and gentlemen, be sure that you don't forget what you already know. Just because you're using a new identity doesn't mean that you sacrifice everything to that new identity. You still use all the arithmetic and mathematics that we've already learned, which really makes problems easier. So don't make the problem unnecessarily difficult by avoiding what you already know. Now, what we see here is that we need to get the arguments aligned. And so you have that really nice, remarkable formula that I keep saying it's remarkable, the tangent of the half angle. So this would be a way to basically force the zero product. The zero product law is really what we depend on to solve equations in mathematics because it does simplify the work, or at least get us to a point to where we have something that's usable. So we can make this substitution and then factor the sign. And again, we're doing some algebra here, so we'll have to make sure that the original equation is satisfied with whatever values that we get for theta. So remember, as you actually make some substitutions and all, we always have to go back to our original equation and make sure that it's solved, kind of like squaring or whatever. So now we can factor the sine. So this will give us a sine theta, and we have 1 over 1 plus cosine theta minus 1. And let's just go ahead and get a common denominator. This simplifies very nicely. So we're seeing what we have to avoid in the denominator, which tells us kind of what we have to avoid up here. So it's not so bad. So this will be a 1 here in this particular case. Let's see here. So we've got 1, and then we have minus both of these terms because of the minus here. Minus 1 minus cosine theta. And this equals 0. But now, of course, the 1's absorb, and we have a negative cosine times the sine. So equivalently, we have negative sine theta times cosine theta divided by 1 plus cosine theta equals 0. So this is a much more workable solution. And then, of course, if this fraction is 0, it would have to be the case that the at least one of the factors in the numerator would be 0. So that's 0 product. So the negative you can just divide out, it doesn't matter. So we have sine theta equals 0, or in this particular case, cosine theta equals 0. So these are easy equations because these are on the axes. So when we think about zeros for sine, we're on the x-axis, 0, pi, so multiples of pi. So in 0 to 2 pi, we'll have 0 and pi. Now, just looking at those, you can see the 0 is fine because tangent of 0 is just 0, so that's good. But the pi is a problem in the denominator and also a problem here. I mean, we'd have to kick that out. So if you looked here or looked here, either way, it's bad because pi over 2 is a vertical asymptote for the tangent. So we'd have to discard that one. So, you know, not everything we get will work, especially when we do some algebraic modifications like this. And then, of course, with the cosine, we know that's on the y-axis. Those are odd multiples of pi over 2. Again, a very common simple equation. You know, when we're in the quadrants, we have tons of arithmetic. We have Professor Ron's lemma, but we're on the axes, you know, easy. So we applaud ease. So in this case, we have what, pi over 2 and 3 pi over 2. So this is kind of a laid back version because we're just looking in this particular set. We have very simple equations. And now, of course, we don't have any issue here, but of course, this will give us a pi over 4 when we substitute, and then a 3 pi over 4. Of course, the sign is defined for any real number, so we're no problem there. And of course, these are kind of working in cahoots, so to speak. So what we see now is that we actually have 3 solutions here that are actually valid for the original equation. So this gives us 0, pi over 2, and 3 pi over 2. So the idea here is that as we move through these equations, we don't forget all of the tricks and all of the techniques that we used in the previous part of the class, especially with the logarithms and exponents and the algebraic equations. We're still using the same techniques, we just have different objects. You know, before we were using logarithms, base A logarithms. Now we're using trig functions. So the techniques are the same. We just have to, you know, consider the fact that we have the little different objects. So we focus on the unit circle, and the unit circle gives us what we need. So it's a level of abstraction that makes the logarithms, exponential functions, the trig functions kind of difficult, at least more so than than maybe some of the algebraic, though those can pose plenty of difficulties based on what we're doing. So I don't want to say that one is more complicated than the other. Basically, what we have to do is that we become comfortable with concepts the more we use them. So if you take a class on Fourier analysis, you'll get real comfortable with sines and cosines and think they're easier than other types of functions. So it just really depends on how much time you spend in a particular area as to how difficult you might think it is. So now what we want to do is to go back to our roots in algebra. And we want to just think about the term or the phrase conic sections. And why do we study conic sections? And you're thinking, is that just geometry or whatever? Well, the Greeks discovered conic sections, and then the French and the German mathematicians, namely Rene Descartes, coordinatized all of that, so that all of these sections of the cone became algebraic objects, kind of like we think of a circle. It has an algebraic manifestation. And so let's just think about a couple of these that we get. When we talk about the double cone that has two naps, an upper nap and a lower nap, and of course, so when we think of a cone in like a two-dimensional thing, we have something like this, and then we have a lower nap, which is just a reflection of the upper nap. So this is what we call the double cone. So the idea is that if we take sections of the cone, for instance, say we take a section upstairs here, we just only want to intersect the upper nap, something like this. If we intersect the upper nap with a plane, then the cross section, so to speak, the intersection is actually going to be a U-shaped object, a U-shaped curve, which really is a parabola. It's a quadratic. We get something like this. So you look at that and think, well, is that the hyperbolic cosine function, or is that actually a quadratic function? Well, the latter is true, but we're thinking of this very differently. And then we might think, well, again, just look at one of the naps and just intersect with another plane. So if we cut through it, we get actually a closed curve. So this one goes all the way through and creates a closed curve. In this case, we get what we call the oval. Or of course, if we orient the plane so that it is orthogonal or perpendicular to the axis of the cone, we actually get a circle. So we call this conic section a parabola, and the other section we call an ellipse. So something like this. We get an oval type structure. And then of course we're thinking, oh, this is the more general case of the circle. So depending on how we intersected the cone, we could get an object that looked more circular, or we can orient it a different way and get more of an oval type appearance. So then with the parabola, we don't really have that, except for the fact that we can orient differently to make it maybe a little wider or more narrow or whatever. So we're thinking, okay, that's reasonable. So the Greeks came up with this, and they came up with all the wonderful reflective properties and characteristics that these conic sections have. And the first two we're going to do today. It's amazing what they were able to discover. And then of course, if you go to natural science museums, they have the conic sections all shown around through museums. Like they'll have rooms that are in the shape of ellipsoids. If you go to Salt Lake City, the Mormon tabernacle where the choir sings is in the shape of an ellipsoid to have the just magnificent acoustics. It's amazing that the properties of the conic sections have been around forever, and physics, mathematics, engineering utilize them. The lights on your car utilize the reflective properties of the parabola or the paraboloid. And our car speakers, the same thing. It's amazing what the conic sections do. So if you ever have extra time, investigate the conics, and you'll never be bored, and always fascinated. So what we want to do, I've got a diagram page that I've already worked up, but I'm going to reproduce all of that for the ellipse, but the parabola is fairly simple. So what we want to do is to say, take the Rene Descartes approach. Okay, so we've got this curve here, we've got this curve here. We're in a pre-calculus class, and we're going into calculus. So if we see an equation, we need to know when we have a parabola, and is it going to be like what we did in college algebra or similar to it? And we need to know when we have an ellipse, is it going to look like the equation of a circle? Because we know what that looks like. And then we're having to think, well, it should be very similar if the circle is going to be a special case of this. So to answer your question, yes, yes, and yes. And so let's see how that comes about. So conic sections, sections of the cone. Now, this first diagram here I've written out, it's very simple. And I want to talk about this, then we'll just kind of redo this completely for the ellipse since it's more complicated. But this is a very simple structure. And what I want to do is kind of start out with this and work through this to kind of set you up very well. So when I do the ellipse, you won't be looking at what I'm doing like it's crazy. So I wanted to kind of give this to you in a complete manifestation first, and then talk through it so you can see the type of technique I plan to use for the ellipse. Now, we know how we can generate the parabola using a section of the cone, but we need to talk about it algebraically. So we set up this definition. I want you to know these definitions. So for the parabola, thinking about an algebraic object, we say a parabola is the set of points in the plane equidistant from a fixed point and a fixed line. Now, that's not exactly like what we thought about when we were taking the section of the cone, but the actual algebraic definition of this will give us a definition that the cone gives us, but in a way that we can work with. And we're thinking, keeping our fingers crossed, that we're going to get what looks to be a quadratic equation so we can breathe a sigh of relief. So how do we do this? Well, we look for simplicity, and this is the best place to start. So we're thinking we want to make sure that our equation is as simple as we can make it. So we want to confirm or guarantee that the origin 0, 0 of the coordinate axis plane will actually be a point on the parabola. So we need a point that's equidistant from a fixed point and a fixed line. So here's the notation. We're going to call the fixed point the focus, and we'll just use F for that. And we're going to call the fixed line the directrix. Very old term, directrix. Sometimes it's pronounced directrix, but I say directrix. Now, if we think about some non-zero number p is going to be kind of like the parameter for the ellipse. We're going to say, okay, a non-zero p doesn't have to be positive, it could be negative. We're going to just go ahead and orient. So we're focusing on this point being on the ellipse, on the parabola. So we're going to pick the focus to be on the y-axis, 0, p, that point right there. And so in this case, we're taking our p to be positive just because it's convenient. And then if we reflect that point in the x-axis, we end up down here at the point 0, p. And we're going to draw our directrix right through that point, that horizontal line that's parallel to the x-axis. So you're thinking, all right, well, okay, that'll work. So now we can see that this point here is a distance P, absolute value of P, if you want to just be specific, a distance absolute value P from this point, and the same from this line when we think of the perpendicular distance. So we've got a point on the curve. So, okay, that's a start. So then we're thinking, okay, well, this particular parabola or the curve, we know what it looks like. So we just kind of sketch out, keeping in mind that we want this distance here between the focus and the line to be maintained. So I just sketched a red curve, parabolic in shape, and then said, okay, here's an arbitrary point, XY, on my parabola, so that the distance from P to the focus is equal or congruent to the distance from P to the directrix. Now, that's the coordinatization part. So again, the point XY is arbitrary, X comma Y. But as we drop the perpendicular to the line, we get the point X comma negative P. So Y equal negative P defines all the Y values. So we call this point D X comma negative P. And of course, the focus is 0 comma P. So the reason I wanted to start with this is because it's so much simpler. I've written a whole lot here, and I'll say more about the other stuff. But the main thing is that we've used this squared distance before, especially with the law of cosines. And so I thought this would be a very nice way to introduce this. That's why I use these arguments throughout the course before the conic section. So when we get to this, this is something you've seen several times before. Now, we don't have a complicated situation at all. We just have this distance equals this distance. And so we can just look at the squares without having to bother ourselves with square roots, unlike the ellipse where we have to do the square roots. Now, so we have the distance between P and F, which again, we say X minus 0 quantity squared, which just gives us X squared. And then we say Y minus P quantity squared, which gives us this. And then we look at these 2 points, and we have, and I wrote this out, X minus X, that's just going to be a 0 squared, so that won't be any contribution. But here we have a Y minus a negative P, so that's Y plus a P quantity squared. So this is even easier than the law of cosines. But the beauty of this is that with this definition, we can make the parabola, that curve, algebraic. So this is an equivalent rendering of the parabola in terms of Euclidean distance, which then can be converted into an equation or algebra. So geometry, algebra, we combine the two. So now we just say, okay, well, there'll be some terms that absorb. And so we expand this. This will give us the Y squared. Then we hit this negative YP with a 2, expanding the binomial. Good old binomial theorem, my friend. We're going to do more with that at the end of the course. And then the P squared here. Now, on the other side, we only just have this term because this is 0. So we get the Y squared, the 2YP, and then the P squared. So again, this argument very much like what we've done in the past. And now, you know, we're like, okay, great. The Y squares absorb. Always underline or put boxes around them. That way you can verify to yourself that they absorb. Don't put the slash lines. You know that's no good and it's horrible notation. I keep saying that because I don't want you to do it. And the P squareds absorb. So what's left? Well, notice we have the X squared, and then we'll get the Y over here. So we'll add the 2PY to the 2PY here, and we get this very simple equation. But again, Y for YP equals X squared. That's quadratic. That's a quadratic curve. So we, good. We know about these. Now, why is this better? Basically because this just says, you know, you can orient the parabola any way you want. I mean, we can have the parabola running upward or downward or right, left, and then of course we can shift it around like we do any function. But now we're just thinking of this as a curve. And then of course, if we wanted to, and if we have time, we could even rotate it, which is a much more complicated situation. If I have time to talk a little bit about that, I will. It'll just be a time crunch at the end of the course. So now when we look at this, we're thinking, okay, well, just like with the circle, we have what we call a standard equation. So then we say, okay, so x squared equals 4py. And so whatever we do, if we look at an equation and we see, oh, there's a square term and there's a y term, isolate the x squared, and then the coefficient of the y term will give us the 4p. And in that, we have the p that defines the parabola. So the p is the important part. It's what basically makes a parabolic curve unique. So this is very different approach from what we had before. Really, the parabola came first, and you know, when we talk about quadratic functions, we just say, oh, by the way, the curve is shaped like a parabola, because it is a parabola. So it's probably better to start with this, but that's not how things work out in algebra and pre-cal. So when we look at all of this summarized, so to speak, we just take what we started with. That is, once we have this equation, we can determine p, and then of course we've set up our focus to be on the y-axis, so we have the focus 0, p. The vertex will be what we always think it is. In this case, it defines the minimum value. That is, the y is the minimum of this function, so that hasn't changed. Again, the ordered pair here defines the occurrence of the minimum value, being the y coordinate here. And then we say, okay, well, let's just copy what we did here. Y equals the additive inverse of p is the directrix. So all of this is really what we started with. So none of these objects right here are new at all. We started out with those. So how do we get these three guys here? Well, that's a freebie. We just figure out what p is. Once we have p, then we can write the focus and we can write the directrix. Now, there's one other piece of information here that the Greeks actually came up with, that Dr. Stewart includes in his textbook. It's called F period D period, focal diameter. Focal diameter. Why do we care about this? Well, let's just look. Notice, and this is why I drew this out here. So when you make your note cards, this is what you need to have on it, just like your trig identities. If we take a line that intersects the focus that is parallel to either the directrix or the y-axis in this particular case, as it intersects the curve, what we're going to see here is that this is a point on the curve, and the distance here would necessarily have to be 2p, p to here, 2p. So this coordinate pair here is 2p, comma p. But this is symmetric by our convention here. And then, of course, this point over here would be negative 2p, comma p. So this is often called the latus rectum, this segment right here. We just know that the length of it is 4 times the absolute value of p. That's called the focal diameter. It's a distance. And so you're thinking this would be a really cheap way to get 2 extra points on the curve. Once you know p, you can just do twice p, comma p, and negative twice p, comma p. Boom, and you got 2 free points without having to worry about looking at the equation. So that's a plus. I had a student one time who made this comment several years ago. Well, we can use the focal diameter to get points. I said, you're exactly right. I said, good for you. And anything is better than having to just wade through, well, let X be this, find Y or whatever. This just gives you a free 2 points, including the vertex. So you've got 3 easy points. Now, if you like, ladies and gentlemen, you can just place the absolute values about the 4P. If that's kind of awkward to write, you can just slap the absolute values on the 4P. So we see from the standard equation, we get the 4P for free. Whatever the coefficient is of the Y, we get the 4P for free. And we take that coefficient, slap the absolute values on it, we have the focal diameter. And if we want to find P, we just divide it by 4. So the parabola really, if it weren't for the directrix, would be kind of simple, but you've got that focus, you got the directrix, I mean, you got the focal diameter. So it's a little bit more busy than maybe we'll find with the ellipse. But the idea here is that we're getting all of the attributes that we have for the standard quadratic function. We're just looking at it a little bit differently, and it's a little bit more general. So let's just think of what this means. What if we had started this problem out and we tilted everything? That is, we put the focus on the x-axis. Would it matter? No, not at all. We just switch the x's and the y's. Let me show you how to do that. We don't have to reinvent the wheel. We do the work the first time, and then we just, what is it, ride the wave, so to speak. When you're riding the coattails of someone else, you're following their glory and not having to do the work. We don't want to do that very often, because we want people to know that we work hard. But when it comes to mathematics, you use my mathematical techniques, because I want you to share the math with everyone and make the knowledge of math better. So let's just say that we do this. Switch X and Y. So say we start out with the same setup. Nothing's new here. We just say, well, let's just think about putting the focus on the x-axis. No difference, just keep it real simple. So if we do it this way, instead of doing 0p, let's just do p0. And we'll just have it open to the right here. It could open to the left. So we have f. Let me write this over to the side. So we'll have f p0. And then we can do the directrix. So we've got the point 0, 0 here. We can do the directrix, the line here, x equal negative p. So now we have a vertical directrix. So we have x equals the negative of p. So there's nothing sacred about putting the focus on the y-axis. So we can interchange the x and the y and get a new set of equations when the orientation either opens this way or this way. And so now, if you want, we'll just kind of do what we did before. We'll go ahead and get arbitrary points. Just kind of space it out. So we can have a curve that opens like this. And so now, do the same thing we did before. So now we've got the point P. So this will be P, comma, 2P. Here our P is positive because we're on the positive X. And this would be P, negative 2P. Okay, So those are two free points using this as the focal diameter. We'll just do 4p in the lazy notation. This is focal diameter. So the thing is, we don't have anything new here. Now we just say, okay, now we have y squared equals 4px. We don't have to rederive anything, just replace x with y and vice versa. And then the focus now is on the x-axis, and the directrix is now a vertical line. And then, of course, focal diameter does not change. Right there. So once you set it up for a focus on the y-axis and do the Euclidean distance, which again, very straightforward, you can now think, okay, well, what if we had just decided to put the focus on the x-axis with the same conventions? We get the same set of equations with the x replaced with the y. So the idea here is you're thinking, well, we could, the next step after this, once we get through the conics, is we can move them around. We can do translations. We can move the vertex, if you will, and I'll go ahead and just write vertex that we get that for free, right? 0, 0. But now this is not a function unless you break it up into pieces, okay? So this branch is a function and this branch is a function, but together it is not a function because you've got the same input producing two different outputs. So again, you can still use algebra on this. We then think, okay, well, if we translate things around, I mean, you know, we could also rotate them too. That's another object that a strategy that I talked about that is available to you. So this is a more general setting, but not a difficult setting. So again, think of this as the kind of the standpoint where we need to start when we want to talk about conic sections, and then we see that the conic section has an algebraic equivalent that's a quadratic. And what we're going to find is that the equation for the ellipse and the equation for the hyperbola will have quadratic forms. That is x squares and y squares in them. So that's a relief. And then, of course, if we extend them to three-dimensional surfaces, they are still quadratic in nature. We call them quadric surfaces. So that quadratic form is always available to us. And that's something that we hopefully have a little bit better understanding of. So what I want to do now is just do a couple of examples with this. So what we're seeing is that the idea of working with the conics usually makes us think about what we've done before. And then we think, oh, okay, so if I'm looking at this quadratic function now, I can think of it as a parabola. And I've got some different ideas that I could think about, especially if you start investigating the reflective properties, which if you have time, you should look into. They're fascinating. Now, let's do an example where, for instance, we want to compute, let's say, the focus, the directrix, want to do the focal diameter, and we'll just write down vertex. We already know what that's going to be, and see what we get. So here's the equation. X equals negative 2y squared. Now, we know this is parabolic. That is, this equation, though it's not in standard form, we can put it that way. We can get a y squared equals 4px. So the first thing we do is put this into standard form so we can divide by a negative 2. So y squared equals negative 1/2 x. So this is what we're looking for, 4px right there. Okay, so that's the easy part. We just have some standard equations now that are easy to manipulate. So you're used to that. You do the transformations, all the algebra we do. So now notice this implies that 4p is the coefficient of x, which is -1/2. So now what does this give us? We can solve for p. Divide by 4, we get -1/8. And then, of course, if we want the focal diameter, you just take the absolute value of 4p. That's why I like just slapping the absolute values on it like that. It's a little bit easier to write. Let me move my cursor over. And so this will give us the absolute value of -1/2, which is 1/2. Okay? Now what we're seeing here is, since the y is the square term, we know in this case that the foci are on the x-axis like we just did. So we have the focus is going to be p comma 0. So focus will be -1/8, 0. So this is like the label for the point in the actual coordinates. We do that a lot with analytic geometry. It's a lot to write, I admit, but it's helpful. And so now if we look at the directrix, we know directrix is x equal the additive inverse of p. So that means we have to take the negative of -8. So this gives us x equal 1/8. So there's our directrix. There's our focus. Okay. And of course, we already have the vertex as the origin. Now, if you like, what we can see here, when you think about the focal diameter, we want to go up, absolute value of 2p, and down. So here, if we take the focal diameter, and divide by 2, we get 1/4. So we can get 2 easy points just using the focus. We can go up 1/4 and down 1/4. So this will give us -1/8, comma 1/4, and -1/8, comma -1/4. So if you have to plot something in WebAssign, that gives you 2 free points. Okay. So now if we want to sketch, and we got really tiny numbers here, but that's okay. We can use a scale that will make it easy. So let's just get a simple sketch. And notice the focus tells you where it opens. We know that we got the negative here, so this is going to open to the left, but we don't have to guess. We could just use where the focus is. The curve always encloses the focus, so to speak. So now we've got 1/4, 2/8, and so 1/8 and stuff. So let's just do like 1/8, 2/8, 1/8, 2/8, kind of like that. Keep it simple, nice and spread out. So we'll just say this is 1/8, 2/8, etc. And so our directrix, vertical line, so we have x equals 1/8. And then we have the focus, -1/8, 0. So I'll just say focus, -1/8, 0. Now, there's your 8 there, -1/8. And so if you like, we can go ahead and mark this off, -1/8, 1/4, right here. And then we'll mark here. And -1/8, -1/4. There's the vertex there. Do the same here. There. So again, that's not Rembrandt. It looks more like a crab, but whatever. I want to get any awards for that parabola. But what we can see here is now we can notate these points. and this is going to be negative 1/8, 1/4, and here negative 1/8, negative 1/4, just to get some simple points. And then of course the vertex 0, 0. So this is a more generalized view of the quadratic function, again using the focal diameter, which is 1/2, so 1/4 plus 1/4. So you can see that when it comes to doing quadratics, we can look at them a little bit differently now. And so if you like, and I want to mention this, we can think of this as being a function in x if we want to split it up into two functions, thinking as x is the independent. So by the square root property, we can say y equals plus or minus, and then I'll just do negative x over 2 like this. And so this would, because of the negative, we see that the domain runs this way. So the domain for both is negative infinity to 0. So thinking of these as functions of x, so we could look at the upper curve as y equals the square root of negative x over 2, and the lower curve is y equals the additive inverse of the square root of negative x over 2. So again, algebraically, sometimes this is something we need to do to break this up into two branches, so that this parabola defines two branches that are functions of x. So that you've done this before. It's just that normally you start with the square root function, or you start with a quadratic and use the square root property, but usually not in this type of environment. So we're still doing the same thing, just from a little bit different perspective. So all the stuff that we've done before, we can still do here. We could have started out with these equations, and it'd be like, well, that's kind of odd. It looks like we've got a reflection in the x-axis, and then we've got a stretching by a factor of 2 because x is replaced with 1/2 times x, so we can look at this as just a standard transformation problem, which is old hat for us. So we get to everything and see that it's all connected, but actually looking at it this way gives us a different perspective, which may be helpful in a class on curve theory or in a physics class or some other class. So how you look at things is actually very important in mathematics. How you lower the level of abstraction so that you understand what the objects are. Okay, so now let's look at an example before we get to the ellipse, where we might just have a little bit different hypothesis. For instance, maybe we're given some information, enough information to actually write the equation of the parabola. So here's an example. So say we have, of course, we've got the vertex of the origin, and we're given that the focus is negative 1/24, that's the x coordinate, comma 0. And we're asked to determine equation of the parabola. So we're told that this is basically the focus of a parabola. So determine equation of the parabola. So now when we look at this, we're thinking, okay, well, the equation we have f p comma 0. And so we see that the focus here is on the x-axis. So this implies that p is negative 1/24. So we're thinking, oh, well, that's good because that's what we need for the actual equation to make this work. Now, when we think about this, we're thinking, okay, so if we're on the x-axis with the focus, this gives the following equation. That is y squared equals 4px. So if we have the p, we have the equation. So the p is what uniquely determines this particular conic section. So that is what y squared equals 4 times negative 1 over 24x. And of course, 4 into 24 gives us a 6. So if and only if y is equal to negative 1/6 x, or y squared. Or if you like, you can make it look even nicer. Just throw the negative and the x into the numerator. Do it like that. So when it comes to parabolas, the p is what gives you all the information. Because when we set up our convention, the p was tied to the focus, and the p is tied to the directrix. So that's the fixed point and the fixed line. So the idea here is that we make the problem user-friendly by convention, and then if we like, we shift things around, translate, and if you like, we rotate. So the conic sections, again, just another mathematical idea that have gained traction because of all their wonderful attributes that we use not only in mathematics, but in physics and engineering. So they're kind of here to stay. And then they make really good calculus problems too. So we kind of can't get away from the conic sections. So a simple problem, but a fun problem. Now, what we want to do is talk about the ellipse in the same way that we discussed the parabola, but we want to kind of build this because now that you have the experience looking at the parabola, the ellipse, though it's a little bit harder to derive, it's really simpler. And you're thinking an ellipse, you know, should have a form that looks like a circle. So whatever we are able to derive, we should be able to get a circle out of it. So let's just look at that. And let's look at the definition for the ellipse. So I wanted to get our feet wet with the parabola because it's a little bit more straightforward so we could stand the ellipse, so to speak. So let's find an algebraic definition of the ellipse. An ellipse is the set of points in the plane, the sum, this is kind of different, the sum, and this is going to help us set up the algebra, the sum of whose distances from two fixed points. And of course, we're going to put those in a way that they're easy. From two fixed points is a positive constant. So if we're thinking simple, but also thinking enough generality here, we can put the two fixed points anywhere we like, and we can orient them symmetric to the origin to keep it simple. But then this positive constant maybe should involve another parameter to keep it kind of general. We don't want it to be so simple that we just end up with another circle. So the key here is a little bit of pre-planning. So the convention is to call the 2 points, each of them a focus like we did with the parabola, but the plural will now be foci. So what we can do is fix a C positive and then orient the foci, for instance, on the x-axis so that they're a distance C from the origin. So get a nice symmetric setup for the two fixed points. So we'll have F1 will be negative C, comma 0, and F2 will be C, comma 0. Then I'll draw a little picture of this. So we're gonna take our two fixed points to be very simply set up on the x-axis, and then you're thinking we'll flip it and we can put them on the y-axis to get another set of equations like we did previously. And now for the positive constant, we will fix, these are common notation with this, we'll fix an A positive and set positive constant to be 2A. Now, the 2A is just for convenience. Again, the idea of analytic geometry didn't come up overnight. And so you're thinking, did someone just come up with this right away? No, this gets evolved. So the Greeks didn't think this way. They thought in terms of geometry, but they didn't have the coordinate geometry and the algebra that we have. But even though they did brilliant work, and you know, who are we to criticize? We're not criticizing. We're just saying they did everything geometrically, and it was amazing what they did. We like the algebra because we understand it. I mean, I guess we have a society that seems to like algebra pretty much. And so now we combine the conic section with the algebra just like we did before. So what is this going to look like? Well, we can just kind of orient everything and then see that if we set this up with the definition, with the Euclidean distance, we should be able to evolve some type of general equation like we did before. So now, of course, we could say here is F2, which is C, comma 0, and then the same distance over here, the distance C, will be F1, negative C, comma 0. And then, of course, this is where this 2A is very useful. We've got a point right here. For instance, that would just make this distance A and this distance A to satisfy the definition. So again, picking a real simple point, we're thinking, okay, well, if this is the case, then the 2A is bigger than the 2C. So this would imply that 2A is bigger than 2C, and so A is bigger than C. So if we're going to set up our convention this way to satisfy this, then these two fixed numbers here will have to abide by this inequality, and that's important. So that's going to be an algebraic restriction that we have to respect. If we don't respect it, it's kind of like not respecting the arithmetic of the unit circle. Our problems become wrong and messed up, even when we don't want them to be. Sometimes we do respect it and we just make mistakes. So the idea here is that, okay, so if we were going to do a more general setting, we're thinking, well, the curve would have to start moving out this way. Same here. And then eventually making its way down in order to preserve this definition. So we're thinking we're going to get a closed curve. Well, we'll let the algebra tell us. So at least for now, we look like we're going to have something like this. And the algebra will tell us eventually that it will close the curve just like a circle. So what we can do at this point is just pick an arbitrary point Pxy, and then think of the distance from each focus. That distance from P to F1 and the distance from P to F2. So now when you look at this, you're thinking, okay, well, we can't avoid the square roots here like we did with the parabola because the equation's more complicated, the definition's more complicated, but we can avoid all of the letters until we need them. What I've tried to do here is simplify this derivation so that we don't get lost in all the letters and then put the letters in when we can work with them easily. So now what we can say is that the distance between P and F1, the distance between P and F1, sum, right, plus the distance between P and F2 must equal the positive constant 2a, the sum of whose distances from two fixed points is a positive constant, okay? So if this point is on the ellipse, the sum of the distances from the two foci must equal 2a. Amazing. Again, the idea here of the equivalence between the conic section and the algebraic definition is immense. So we can't take any of this for granted. There was lots of work that was done to set up these conventions. So now it's just gravy for us. We just have to verify things and then move forward with it. Now, the idea is now we're like in college algebra class. So we want to isolate one of these D's because it has a radical and square it to get rid of it. And then isolate again, and then put in all the letters. And then we can square one more time. But at this point, putting in the letters now would be a complete waste of time. So let's isolate this. Let the algebra do the work until we're forced to put in the Euclidean part. So we get 2a minus d fp comma f2. Now square. As we square symbolically, we're going to get rid of the square here and then introduce another square here with a non-square. So square. This gives us the square of the distance from P to F1 equals, now squared the binomial. So we get 4a squared. Hit this with a 2. So we get 4a times the distance between P and F2. So we're just squaring the binomial, square, square, and then the product times 2. So that gives us a negative 2a times the distance with another 2 gives us the 4. And square that distance, we get rid of the radical. So at least symbolically, we're getting rid of squares or square roots. And then now notice the only thing that has a square root in it right now is this term right here. All of these are devoid of the square root. And so let's isolate that, throw everything on one side, fill in the numbers, see what absorbs, and then square one final time. So now take this over, we get 4a distance between P and F2 equals, now what's left? Well, we've got these two terms and we subtract this term. So we've got 4a squared plus the square of the distance from P to F2 minus the square of the distance from P to F1. And now we can go ahead and substitute the Euclidean part because these are all easy. And then we can figure out what stays and what goes away. So we have 4a, and now I'll use the bracket with the radical. So the distance between P and F2, so this will be x minus c, quantity squared, and then y minus 0, so that's going to be y squared to the 1/2, because that still has the radical because there's no square there. And these, no radical, so 4a squared. Now, of course, here, this is the same one, P to F2. We just did that, so we just copied this right here without the square root because it's squared. So we got plus x minus c squared plus y squared. So we just copied this without the radical. And then we've got the minus here. So we're going to have to distribute the minus. So P and F1. So x minus the positive C, minus the negative c is plus. So we get x plus c squared, and then y minus 0 squared, so plus y squared. Okay? So now what does this give us? Let's just kind of reduce all of this stuff. So we get 4a, and we get x squared, expand 2xc plus c squared plus y squared to the 1/2. So you see why I didn't substitute the numbers until I had to, the letters, because it's a lot to work with, but we can do it. So we get 4a squared, and so we have what? Plus x squared minus 2xc plus c squared, and don't forget the y squared plus y squared, that's just hanging out, then minus. Now what do we have here? Let's just go ahead and write up what we have here. This is easy. Do a little sidebar. So this will be x squared plus 2xc plus c squared plus y squared, all of that. And we just have to slap negatives on it. They all get negatives. So we'll get a negative x squared. We'll get a negative 2xc, a negative c squared, and a negative y squared. So that was easy. That's why I'm saying we needed to substitute here, because for this to reduce, I mean, you're thinking, my gosh, Professor Ron, if we have to square again, we've got to square a trinomial. Friends, you don't want to do that. There's nothing wrong with it, but it would be too much work. So this is why we do this at this point. So now notice the x squares absorb. Remember, when you absorb in your work, you can underline or put boxes around them. No slash lines, please. I have taught you better than that. C squares absorb. Y squares absorb. See what I'm talking about? Everything's going away. So now we have a 4a squared, and we get 2 copies of the minus 2xc. So that was worthwhile. So we get 4a squared minus 4xc. Notice the 4 is going to absorb, and we'll absorb it because we like smaller numbers. Now we divide by 4. All the 4s are gone. So this gives us, and then of course, once we divide by the 4, we can square again, but I'll wait to do that. So we've got equals a squared minus xc. So notice, always get rid of the extra stuff. Get rid of the extra stuff. It's just in the way. Now, like I say, we squared here. We square one more time to get rid of that radical. So write square. Now, when we square this, that radical goes away. So that's an easy square, and we get an a squared. So a squared times x squared minus 2a squared xc plus a squared c squared plus a squared y squared. And square the binomial here, binomial, square the binomial, we get a to the 4th minus 2h squared xc plus x squared c squared. So that binomial square is our friend, and we do the general binomial, at least for the positive integers. That'll be fun. Then when you get to Cal 2, you do the more generalized binomial, and that's difficult. So we have to start somewhere. Now notice, if we look here, we do get these to absorb. These absorb. And everything else is what we need to finish off the proof. So get all the x squares together, all the y squares, and the riffraff terms come over here with no x's and y's. So we have what? A squared, x squared, and I'll do the c squared first, minus c squared, x squared. So check, check. We've got a y squared term here, and no others. So we've got what? Plus y squared. And then we can just move this over. This is the non-xy term over here. So this will be a to the fourth minus a squared c squared. So check, check, check. Now notice this just factors the a squared times a squared minus c squared. But remember, a is bigger than c, so that's a positive number, and we need that. So now we're getting somewhere. So what we're going to do is do the same over here. So this gives us x squared times a squared minus c squared. Let's see here. So we've got the a squared, and let's see, what else do we have? Yeah, that'll work. And then we have plus here with the y squared. Let's see, did I drop it? Oh yeah, here, let's see. I left out my a squared here. I thought that was lost an a squared. There's an a squared right there. Plus a squared y squared. I need that. I need that a squared. Otherwise, my derivation doesn't work. Equals a squared times a squared minus c squared. So now let's divide. So it looks like we've just been court reporters for most of this problem. So now let's divide here by a squared minus c squared times a squared. And this is what you all always do. You do something like this. So you say a squared, so like we're, back in algebra 1. To get a 1 over here. Right there. So now when we divide, the a squared minus c squared is absorbed, and we get x squared over a squared. And then here the a squared is absorbed, which I needed, and we get y squared over a squared minus c squared. And then, of course, that's just the same term over the same term, which is 1. So that's what we want. Now let's finish it off. So remember, A is bigger than C, so set, this is what the convention is to make this more user-friendly. So now we'll have a way to combine the denominators with the C and the A. So we're going to set B squared equal to A squared minus C squared, which means equivalently that C squared will always be A squared minus B squared for the ellipse. So now, equivalently, we have exactly what we thought we would get. Even though the derivation is harder, it's simpler than the parabola. So the idea here is if we see that the A and the B coincide, we get a circle. So this is a generalization of the circle. So if, again, like I say, if the A and the B coincide, we don't get an oval. I mean, here we were pretty much getting the oval. So as we keep extending it, we get the oval and bring it on around. So like this, etc. Like that. So the idea is we actually came up with an equation that makes sense to us. Now, from our convention, in this particular case, the A will be bigger than the C, so we basically have C squared equals A squared minus B squared, and then with this convention, we'll say that A squared corresponds to larger denominator. And if that's the truth, that will tell us which axis, the horizontal or the vertical, contains the foci. And so now all of these numbers are positive. So A is positive, B is positive, and C, all positive. So when we take square roots, we don't have to worry about negatives. I mean, unless we're just plotting the foci, but the number itself, by definition, is positive. Okay, we fixed the positive c, we fixed the positive a, and if b squared is a squared minus c squared, by definition, it must be positive. So it's going to be the y-intercept here, plus and minus. So here we will establish these as being positive numbers that we can slap a negative on if we're looking for a point. And so now we'll say the major axis will have the coordinates negative a to 0. So the first vertex and vertex 2 will be a to 0. So we're gonna say that the intercepts along the x-axis here will be called vertices, and we'll have a length of 2a. The minor axis will not have special coordinates. That'll just be the minus b and the b. So 0b, 0 minus b, and we'll say the length will just be 2b, as we've established these to be positive numbers. And then, of course, the focus, or the foci, will just be focus 1, negative c, 0, focus 2, c, 0. So, like I said before, we already established these from the very beginning. So that's nothing new. That's like, well, we knew that. But now we see, but from this definition, if the y is 0, then we get the x-intercepts, a and negative a, okay? So we allow this notation to call these actual intercepts of the horizontal axis, we call them vertices. So we'll say vertices, like the vertices of a triangle. And so that's pretty much it. Now, like the focal diameter, we have what we call eccentricity. Before I do all that, let's just go ahead and finish the picture. So we'll just complete the picture that we started with. It's kind of a general rendering. So here we have vertex 2, a 0, vertex 1, negative a 0. We have our b, negative b, and then we have the foci that are interior. Focus 2, c 0, focus 1, negative c 0. So we see in this case that the ellipse is pretty simple. It's just like a circle. We don't have a directrix, we have a closed curve. The parabola is not closed, the ellipse is closed. So you're thinking, all right, you can travel around the ellipse, like you travel around the unit circle. So that's some simplicity there. And we have a lot of nice symmetry. Now, another thing that we get from the ellipse, like we get the focal diameter, we call it eccentricity. So we define, and this is another thing I think the Greeks came up with, define eccentricity. Eccentricity, we need a T here. Eccentricity. And this will be denoted with an E. It's not the base E. Please don't call it that, but we use E, unfortunately. We should maybe call it an uppercase E, but unfortunately, this has stuck. It's not base E. This is going to be C over A. Now, why is that useful, and why do we even care about this? Well, C is what? The square root of A squared minus B squared. And if you want to extend the square root, we can write A as the square root of A squared, because again, they're positive quantities. We don't get absolute value. So we can do something like this using that. And so now you can think, okay, well, divide by A squared, we get 1 minus B over A quantity squared. And so now you're thinking, if A is close to B, A is always going to be bigger than B, but if we say A and B have similar size, then this will be closer to 1, and we'll think that we have 1 minus 1. So basically the eccentricity will be close to 0, or closer to 0 than it is to 1. And then we think, oh, this is circle-like, circle shape. So when we look at this, if the A and B are close in magnitude, then we have less oval shape. We have more circular shape, where the A and the B have similar magnitude. So this would spread out a little more. Now, of course, the A is bigger. So say it's a lot bigger than the B, or noticeably bigger. Kind of like this. Then we're thinking, if this is a lot bigger, then this term is small. This is closer to 0. And so we'd say eccentricity would be closer to 1. By definition, we see that the eccentricity runs between 0 and 1. Okay? And so by definition, if we look here, A is always bigger than B. So this, we're not going to get equality here, but we know that the eccentricity lives between these two numbers. And so if the eccentricity is closer to 1, because A is a whole lot bigger than B, we get the oval shape. Okay? So this is just a little aside. WebAssign will ask you to compute eccentricity. Really, you just know that eccentricity is C over A, and you can, if you're in a class where, your physics professor says, well, what's the eccentricity of this ellipse? And you say, oh, well, it's 1/8. And then you'll say, oh, that's more of an oval shape, sir, or ma'am, or whatever. And well, how do you know that? It's like, well, I took Professor Ron's pre-cal class. Oh, good for you. Oh, you passed. Very good. No, I'm just kidding. The thing is that physics professors love physics students who know math. When my honor students would go to physics at the North Campus, they'd always get kudos. Oh, my students know math. And if they would work with Nate, my colleague Nate, in engineering, he said, oh, Ron, your students always know their math. I said, well, good. That's what I want them to know. That way they can win prizes and become leaders in their professions. So this may be kind of silly, but and not that big of a deal. But just kind of look at it as just an extra ingredient that we have with the ellipse. Now, of course, if you like, you can go ahead and flip everything around. So, for instance, let me just give you the equations for this. So I'll say replace x with y. And so now we would have y squared over a squared plus x squared over b squared. And so now the major axis would be vertical. So we'll just say in this case, major axis is vertical. So everything else is the same. The length of the major and minor axes, they don't change. That's the same. The only thing is that x is replaced with y. And so now the foci will be on the vertical axis. So we'll say 0, negative c. F2 will be 0, c. And now the vertices, again, will be on the vertical axis. We have 0, a, negative a, and then F2 or B2, 0, positive a. All right. And then, of course, eccentricity is all the same. No other differences. It just, again, this just gets turned this way. So when we think about it, again, the larger denominator will always denote the axis of the foci. So things just get flipped. It's not an inverse function, it's just a simple way to derive another type of an ellipse that's distributed differently. So basically, when it comes to the ellipse, we see that the A and the B define it. So here we have B2, which is 0A. We have B1, which is 0, negative A. Here we have B, we have negative B. And here we have F2, which is 0, C. And we have F1, which is 0, negative C. So the idea here is it's just like the parabola. We're going to have certain conventions that if the parabola, if the y is squared, then we open to the right or the left. If the x is squared, we open up or down. Here, we look for larger denominator by our convention. The larger denominator claims the axis for the foci, claims the what? The major axis, the longer axis. You don't have major and minor for a circle because they're the same distance. So or the same length. So again, our convention is forcing us to look for the larger denominator to claim the major axis. Okay, so that's our convention. So there's no ambiguity there. Like I said before, once we set up these conventions for the algebra, we must respect them. If we don't, then we start making it up. Okay, so what we see here is that the ellipse is really just what we thought it would be, circle-like. Okay, so let's do a couple of examples. So the reason I wanted to do the derivation here is basically so that you could see, that when we work with equations and all, I mean, let's think about it. Sometimes in math, it doesn't appear that we do things in the right order. We try to do things in a way that the order gives you understanding. Now, there may be some kinks in that, but thinking about it, the conic sections are a little bit more advanced in how we look at them. So I can work through the derivation because I know you've worked with square roots. I know you've worked with distance and quadratic functions. So maybe sometimes we have to move it around a little to make it more user-friendly for you. So just realize that you're not going to see conic sections every day in calculus, but when you do see them, you'll recognize what you have and you'll have to use what you know. I mean, ellipses come up in calculus all the time. And let me tell you, the arc length of an ellipse is a nightmare, okay? An absolute nightmare. In most cases, you have an elliptic integral, which is extremely hard to compute. So these conic sections are not always friendly, but when we do deal with them, in some cases, we can get some very beautiful calculations. Just arc lengths are kind of crazy. So just letting you know, not everything is the rose-covered path, so to speak. So here, let's look at, we want vertices, we want foci, and eccentricity. So, of course, this is for an ellipse. So all of these are pretty much the same, ladies and gentlemen. Once you know the basic attributes of the conic section, you can solve any problem. And so I've got this, so I can figure out the A, or I've got this, I can figure out the C. I have this, so I can figure out the P. I mean, that's basically how these run. So nothing abstract. So say we have the following. We have 2x squared plus 25y squared equals 50. So I want you to get really good at these. So when we start moving them around, you won't have any problem with them. So put all of this on note cards. So now when we look at this, we think, okay, this is not a circle because these coefficients aren't equal. So this is never going to be a circle. So this is if it's anything, it's an ellipse. It could degenerate, and that does happen. But this is most likely an ellipse. So what we want to do is we want to think of one of the standard equations. So if we have an ellipse, maybe we'll have this or the other. So we'll just write down what we know to be the standard form. So the first thing is to get the 1. So let's divide by 50. We don't have to complete the square. Everything's good. So we have 2x squared equivalently, 2x squared over 50 plus 25y squared over 50 equals 50 over 50. Now, of course, this is simple, but you have to get used to it. And here, let me move the calculation this way so I have room to work over there with other stuff. So of course, this will be 2 into 50. That'll give us 25. So these are user-friendly numbers. And then of course, 25 into 50, that gives us 2. And then of course, 1. So now we see the larger denominator is associated with the x. And so the major axis is what? Horizontal. All right, so it's that simple. So now we look at this and we say, okay, well, a squared is 25. B squared is 2. So this implies c squared, which is a squared minus b squared, is 25 minus 2, which is 23. So you look at that and say, okay, well, that's good. So now I can get my A, my B, and my C. So A is 5. B is what? Square root of 2. And C is what? Square root 23. Now, you don't always need the B. We just need the vertices and the foci. So maybe that was overkill here, but that's important. But we do need the length. So we'll say major axis. I'll go ahead and write this. Major axis has length what? 2a, which is 2 times 5, right? So that's not a complete waste of time. That's 10. And the minor, I'll write as minor axis, that has length 2b. So the b is good here. We get 2 root 2. So remember, if you want the length of the major axis, that's twice the A. The length of the minor axis is twice the B, where these are by definition positive numbers. Don't put in negatives for distance, ever. That's such a common mistake and so unnecessary. So now you're thinking, okay, well, we got all the stuff, we got all the goods here. Let's go ahead and write down the vertices. So vertex 1. And usually with the WebAssign, they'll say put the smaller a first or the smaller c. So follow that formatting because they want you to enter the ordered pairs nice and clean. So watch for the formatting. So B1, that'll be what? -5, comma 0. B2, 5, 0. F1 will be negative square root 23. 0, and F2, positive square root 23, 0. All right? So just kind of tabulating these. And then, of course, we can do eccentricity. That's going to be C over A. So that's going to be the square root of 23 divided by 5. So now, of course, these are closer together, right? I mean, these are close together. So if we think about this, when we think about A being close to or whatever, well, look at this. This is not comparing the A and the B. This is close to 1, right? And so when we look here, we're doing this. Because what? A is pretty much bigger than B. I mean, not a whole lot, but it's clearly bigger. So we expect this to have more of an oval shape. So when we compare, we're saying this is a little bit closer to 1. So because the A, well, you know what I'm saying. Let me just say this one more time. This is a little bit smaller. because A is significantly bigger than B, so this will be closer to 1. And so we get the oval. So that's kind of the interpretation I was talking about. Again, not earth-shattering, but why it exists. So we're going to think oval. Now let's just go ahead and get a nice little picture of this. Not Rembrandt, but, you know, decent. So now we've got, let's see, we'll just mark off 5, just kind of guesstimate here. So 5 and -5. So B1, or B2, sorry, 5, 0. And then B1. And now the foci. Again, it's a little bit closer than I'm writing it, but I'm just spacing out a little bit. Okay, square root of 23, 0, and then here. Okay. So let me make sure we got good. Let me move Professor Ron over. A little crisper there with the focus. And then, of course, we've got the square root of 2, so a little bit closer here. So square root 2. So square root 2, negative square root 2. So these are vertical tangents at the intercept, so I don't want to draw them like they're not. That's kind of bad. So there's our ellipse. And then you can darken it in a little bit. All right. More oval-like. So again, the ellipse, again, you're thinking this defines 2 functions. We have an upper arc and we have a lower arc. So if you just a little aside here, we can take this guy right here. So we've got this is a common application. 25 y squared is equal to 50 minus 2x squared. So in this case, we can clean this up a little bit. Let's see here. So now we can say this is what 2. So we have what 25 minus x squared. And so y squared will be 2 over 25, right? So this will give us y equals plus or minus the square root of 2 divided by 5 times the square root of 25 minus x squared. And so the upper arc is the plus root and the lower arc. So for instance, here we see this upper arc is this guy. Y equals the square root of 2 over 5 times the square root of 25 minus x squared. Again, we see the intercepts are 5 and -5, but it's what? It's what vertically compressed. So this is showing us that this is compressing this circle because this number is less than 1. So function transformations all over again. We're not really learning anything new except recasting what we already know. And the lower arc here will be y equals the negative square root 2 over 5, 25 minus x squared. So that's the lower arc. So if you needed to just talk about functions here, you can talk about the upper function and the lower function, just like you do when you're talking about circles. So there's no difference. So the beauty of the quadratic function is not lost in any of this, because all of this is quadratic in x and y. So that's a plus, a big plus. So what I want you to get from this is that this is just like the parabola. You can just kind of beat it to death until you get sick of it. So when you do your WebAssign, you just, you know, if they ask you to go through the laundry list, then do. Sometimes they may just say, well, with this information, find the equation and keep it really simple. So this kind of goes through all the stuff, which is a little bit dry, but you can pick and choose when you're answering particular questions. Okay. So now let's look at another example. Here, let's see here. Here's an example. Let's do a couple of examples where we just have to figure out what the equation is given pertinent information. So here we go. So here, example. We have the foci are what? Plus or minus square root 10, 0. So they're on the horizontal axis. We have the vertices. This is in the shorthand notation, not with the B1, B2, but where you just do plus or minus, you know, but remember with the WebAssign, you have to list them separately. And then it says determine equation of the ellipse. Determine equation of the ellipse. So now you're thinking, okay, well, everything is distributed with the horizontal axis, and here we see A is equal to 8 and C is equal to the square root of 10. And we know C squared equals A squared minus B squared. But then that just says B squared, which was the original substitution, is A squared minus C squared. So now that tells us, so B squared will just be 64 minus squaring the square root of 10. Let me get the cursor out of the way. Will just be 10. So we square this, we get 10. We square this, we get 64. So these are easy numbers. So we get 54. So we're thinking, all right, well, that's fine. So now we know that the major axis is associated with the x term. So this implies x squared divided by 64 plus y squared divided by b squared, which is 54, equals 1. So when you're going backwards, it's not usually as difficult. You don't have to do as much work. I mean, you just basically, you're given here the A and the C, so you can find the B. So for instance, we have a few more parameters here than we do with the parabola. With the parabola, we just really need the P, and we're good to go. But we start off with two fixed positive numbers with the ellipse. So we have to have enough information to figure them out. Otherwise, we can't write the equation. But now, of course, this is a unique ellipse, and we're done with it. Now, let's look at another example. So sometimes the equation or the problem will just ask for, you know, basics. Like when you're doing your trig, they just say, well, what's the cosine of, 11 pi over 4. I mean, things like that where you just use reference numbers and you're good to go. They don't take long. So now let's look at another example. We've got, in this case, eccentricity is 1/4, and the foci are plus or minus 3/4, 0. So in this case, it says write the equation of the ellipse. Now, again, this is like we had before. We have the foci here, so this implies at least that C equals 3/4, because that's how we define the foci for the ellipse. And we know that E equals C/A. So if and only if, what? Flip these two, A equals E/C, or C/E, sorry. Just by proportion. And so now we get 3/4 times the reciprocal, 4/1, which is 3. So this is simply a nice equation or a nice problem dealing with the fact that we know the definition of eccentricity. And so here we have A and we have C, so now we can find B. So we know, same song and dance, we know C² equals A² minus B². Equivalently, B² equals, in this case, A² minus C². So now we have, in this case, A², which is 9, and C² will just be the square of this, which would be 9/16, right? So this is 9 times what? 1 minus 1/16, and that's what 16 minus 1, so that's a 15, right? Now, of course, this is interesting the way it's written here. 15/16 is less than 1. So B² is indeed less than A² as it needs to be, because we know in this case that the horizontal axis contains the foci. So we don't have to really check that, but we want to make sure, you know, it's correct. Even though, you know, like I say, a lot of times you just forego all of that, but you want to make sure that your computations are consistent. And so now you're thinking, okay, well, we can multiply this out. 9 times the 5, that'll be a 45. 4 and a 9 will be 135/16. So this is B². So this is an interesting problem, makes a good test question, because first, you know, you got your note cards and all, so it's not a problem. I mean, you have all your formulas, and so you just say, okay, I know eccentricity, so how do I write the equation of an ellipse? Well, I need to know A and I need to know B. So now this implies that we have what? X² over A² plus Y² over B² equals 1. Equivalently, we have X² over A², which is 9, and then Y² over B², which is 135/16. This equals 1, but of course that's probably not the best way to write this. We need this written in this term, this way, to find what B² is, but then of course we just reciprocate it. And then of course, if you did the reverse problem, you'd have to do what we have here. So this would be 16Y² over 135, and this equals 1. So the idea is, if we have a problem like this, we have to flip it around like this to figure out what B² is, because the standard form requires it. So the ellipses and the parabolas, we just do a lot of manipulation with factors, manipulating coefficients, just like we do with function transformations, just like we do with trigonometry. That's what we do. The mathematics is the art of symbolic computation with algebra, numbers, geometric objects. That's all we do is symbolic computation. And like I say, if you adhere to that, then your work is better. Your work is going to be less error prone, and you'll actually enjoy what you're doing for a change. I mean, math shouldn't be drudgery. And it will be drudgery if you don't spend time on it. But when you spend time on it, it's like actually fun. I mean, it gets to the point, I usually don't characterize math as fun. I characterize it as rewarding. But when you get to the point to where you're doing it consistently, you start to enjoy it and you enjoy the reward of it. So I'll put up an announcement. Basically, the next test will cover through ellipses, and it'll be at the beginning of next week. I'll give you a 2-day window to take the test. And then, of course, you'll have to complete your homework on the stuff we do Thursday. And then, of course, we'll have a lecture next Monday. We have no choice. Normally when you have a test, I don't give you a lecture, but no rest for the weary. I want to get this test in before, and I'll still give you plenty of time to take it. But if I do not cancel the class, I expect you to be here. I always record everything, so if you've just got to sleep in, I understand. But I will be lecturing, and anything that I lecture on, you'll be responsible for. So I appreciate your attendance today. Enjoy the cool weather and enjoy the conic sections, a nice break from the sines and cosines. You need a break from that. I know I beat you to death with it. And if we do say a little bit about rotation, we'll come back to the cosines and the sines, but I'll let you know if I feel like I've got time for that. But I appreciate your attendance today. If I don't see you at my office hours, I'll see you again on Thursday. Everybody have a good day.